Yes, so we have now quantitatively and qualitatively understood what a correlation or correlation coefficient exactly means. Essentially, we have seen that positive correlation is associated with the data having more or less a linear relationship. That is characterized by a positive slope, and negative correlation means there is a linear relationship associated with a negative slope. And all of this reminds us of something we have already discussed in math class, namely the topic of linear regression. And that's why I would like to revisit linear regression in this context, describe the year 2001 and its relationship with correlation in this video. Let's take another look at the example we had back in math class 2. That was the following example. It was about house data, where we look at the size of rent apartments in square meters on the x-axis, and on the other, y-axis, we look at the rent, for instance. And of course what we see here is that it is a positively correlated value. So, the larger the apartment, the higher the price, at least from a statistical perspective. And this can be seen precisely by looking at the trend, which is naturally moving in a positive direction. And if we now recall what the goal of linear regression is, it is to find the trilinear relationship between these two variables. This means finding both the slope and the y-intercept. And we did this by stating that this here, the mean squared error, which is ultimately the square of these distances to the corresponding line, is what we want to minimize. And for that, we have also seen a solution. 2001 Math 2. Let's quickly review that again. So we have the following situation. We have our data x and our labels y, which is a similar situation to what we have in the case of correlation. We have the same number of data points x and the same number of data points y, which are real numbers. And what we are looking for is a function usand. And right now, let's first take a look at what we did in Math 2. In Math 2, we have only considered origin degrees in the formula that we learned. We also learned a trick on how to expand the whole thing, so to speak. But essentially, our formula describes a solution for the slope, where we have the y-intercept, which I will write down here as 0. Well, exactly, and we want this so-called mean squared error to be minimized, which means that this term here should be minimal. And for that, we learned a formula, which looks as follows. Perhaps you remember, we wrote down a matrix X. And this also applies when the X's are in, well, when there are more features. Then, it is indeed also possible to perform calculations with matrices. Or, if we simply look at it in one dimension, we see it approximately as follows. And it looks quite similar. I would like to take a quick look at this term together with you. It looks similar, Yusan, to a covariance, except that here the minus y, that is yy, is missing an xx bar. So if y bar and x was 0, then that would be a covariance. Otherwise, it's something similar, a bit simpler than a covariance. And the same applies here for this term, she. It would also be a variance if it were, again, x, 0. Otherwise, we would have to write x here as well. Yes? So it looks somewhat similar to covariance, but it is a bit different. And it is also relatively clear that covariance and regression have something to do with this slope, because it essentially describes whether the thing goes up or down. And that's why there is actually a formula, which I would like to explain to you briefly, and I also want to clarify the difference. This formula, namely, includes the a part as well, which means that if you want to find a line that is not a line through the origin, but also has a y-intercept, you can use this formula from now on, at least for the one-dimensional case. And I want to briefly describe the formula to you here. So we are here, and actually, you see we can express this whole thing so the a is the slope, and I can write it as the correlation coefficient multiplied by the standard deviation of y divided by the standard deviation of x. And what we see here is that the sign of this term is completely determined by this term here, because Sx and Si are of course positive. And this also shows the relationship between the two quantities of the slope and the coefficient. In fact, they have the same sign, yes. And that is exactly what we expected, because they essentially measure the same thing, at least in terms of the sign. And then there is also a formula for, let's take a look at it, for a, which is then y-ax. We don't need to go into that too much. I just want to briefly touch on this here, so to speak. Why is that? Well, that's because our xe is equal to sxy divided by x times si. And if we then multiply this term here, let me just remove it for a moment. Oops. If we multiply this term here by psi divided by sex, then it cancels out and we are left with sex, which is exactly this term here. So, this is a simple rearrangement of this formula here. Well, and exactly. So this shows the connection between these two concepts. And finally, I want to clarify one more intuition for you about why, when you have this data, the correlation is actually 0. That was our example with the square values, where we already calculated that the overall correlation is 0. However, I want to look at it in another way, namely considering what the best regression through these points would be. One might think that it probably does not go down or up, but rather in some form, meaning it is a straight line, which indicates that the slope of this line is 0. Thus, a is 0, and that means nothing other than that our xe must also be 0, because, well, because these two values here are not 0. And this is yet another justification, perhaps another intuition, as to why the quadratic relationship between x and x exhibits a correlation of 0. Yes, that was the topic of regression and correlation, and in the next video we will look at how to actually use what we have learned so far in an exploratory data analysis with Python. Until then.